We would firstly like to thank those of you that are here today that were also at our presentation in December, and would like to welcome those that are here today for the first time. My name is Danny, this is Carlos and Omar, and together we are Team Sub-Automatic. The goal of our project was to design and build a machine that would fold sub sandwiches. This machine would decrease the turnaround time for a customer entering a major food chain from when they receive their product. Okay? This machine is also to be built using FDA-compliant materials, all the while remaining cost-effective and, most importantly, safe. Okay, so our main appeal for this machine is not that it will replace an employee in these businesses, but instead would free them from performing a tedious and necessary task, improving the overall efficiency of the line because the employee would be able to assist the next customer. This product also has potentially worldwide marketability, and for this reason, we aim to keep the initial price to purchase at a minimum. So this is an excerpt taken from the FDA Food Code, and it states that for materials that are in contact with food, they must not allow the migration of deleterious substances or impact colors, odors, or tastes to food, and under normal use and conditions shall be safe, durable, and be made of substantial weight and thickness. So as a customer, when you first walk into a Subway, for example, you are prompted with a choice of bread, your fillings, and whether you'd like your sandwich toasted or not. At this point in the process, it enters what we call phase 2, in which the sandwiches are folded, cut, wrapped, and placed in a bag and handed to the customer. Where our machine would come in is at the start of phase 2, okay, which would then take care of those 4 steps and allowing it to be placed in the bag and handed to the customer. This would then free up the employee to assist the next customer, shown at the top by the yellow arrow.
So like Danny said, the motivation for this project would be to market this product to franchises like Subway. And as we can see here, Subway worldwide, as of 2012, had 25,500 stores, which is more than double of those of McDonald's and Starbucks. So we have a really wide market globally. And so feeding off of that, we decided to do some research on Subway, and we watched some training videos from corporate. What we found was that when they're busy during lunchtime, they measure the throughput by this ratio, which is units sold per hour divided by the number of employees working. If we can actually one day have a machine like this, then what would happen is we can either increase the units on the numerator, or we can decrease maybe 1 employee on the bottom, which will dramatically increase the ratio for which they base their performance. And as you can see here, corporate tells their associate that it should take about 3 minutes to make the whole process from when you walk in to when you take your sandwich, and that employee should do that task. And this is what we focused on with our design, to have the employee do less, like Danny said, not fold, but come back and start on the next customer.
Now the idea initially brought to us is very simple. A system of plates with a pneumatic, hydraulic, or pure mechanical forms of operation. The sandwich would be placed in the middle, and the hinges around the middle plate would help fold this up. Now the problem with this idea was the hygiene factor. The hinges itself has many crevices in which bacteria could accumulate, causing health concerns as well as safety concerns. Also, one of the main problems with this was high employee involvement. We weren't able to efficiently remove that employee from that task, but still just aid in the task completion. So upon this, we actually did a design revision. This actually went to an electromechanical drive mechanism and extending it for modularity. This would widen our market to mom and pop shops who still wanted this ability, who had lower means. Less employee involvement made a more efficient line, while the only difficulty with this one is the actual implementation. As you see, the belt itself is pretty intricate, as well as actually the drive mechanism itself. So upon this, we did another design revision. This revision, they did 2 separate rails, while a cutter module placed was a lost motion cutter module, did increase the safety hazard. But it incorporated some of the benefits from the previous design while adding a few more, as well as such as the belt drive mechanism, but again, lost motion and high risk. So another design revision was iterated. This made the channels the focus. By doing the channels, we were effectively able to fold this up while still maintaining the drive belt configuration. This allowed us to focus on implementing certain aspects of the previous designs while still maintaining marketability. The only other problem with this one is the expense, complexity, as well as the open drivetrain, which could be exposed to fingers or biomass that can cause bacterial growth. So upon this, and as well as expert advice from industry experts, we came up with this, a modular system. Instead of, we were recommended notches, but we decided to go with actual pin system. To increase the modularity, we went to one rail only, as well as a fully enclosed system, and able to actually be expanded and rotated and actually configured in multiple ways. Now, as I went over the design, Daniel and I will go over a little bit of the analysis.
Okay, so for the first part of analysis, we took a look at our narrowing channels. Okay, the picture on the right is taken from SolidWorks, which just measures our angles, which we call the folding angles. To better explain this, I'd like to draw your attention to the left photo, which is actually taken of our model. Okay, you will notice that the angles A and B, the difference between these two angles is what we call our folding angle. Okay, angles A and B are measured by using the center line of the conveyor belt as the vertex, with the 2 points being the widest channel, the widest point on the channel, on the inlet, and on the exit at the same height of 4 feet. Okay, so the difference between these two angles for our current revision is about 16.5 angles, 16.5 degrees. This picture on the right depicts the top view of our channels, which displays our entry and exit angles. To better explain this, the two pictures on the left will assist me in this. So we modeled it after the leftmost picture, which is a gradually converging nozzle. And we noticed that we did this because it is much easier to pass material through the gradually converging nozzle than the middle picture, which is an abruptly converging nozzle. Okay, so then the next part is we have a conveyor system and we need to deliver power to it. So we decided to use a small 12-volt DC motor. Okay, so the motor that we have, the specifications for this are that it has 500 milliamp stall current and provides approximately 11.5 pound-inches of torque. We wanted to verify this torque rating, so we performed a simple test. What we did was we hooked up a 2-pound weight at a moment arm of 5 inches and then connected this in series with a multimeter to see the current drop. That test concluded that it drew approximately 360 milliamps, well below the 500 milliamp stall current, and also verifying that this motor could in fact produce the specified torque. Now the picture on the top represents the circuit diagram for the way the motor is connected. Go back one more. Okay, the motor is to be connected to the wall directly using a retrofitted Netgear power adapter that we splice the ends to create our own fitting for the machine. This will convert the 120 volt 60 hertz signal from the wall to approximately 15.5 volts DC output at a maximum of 1 amp, which is then connected to a single pull, single throw switch. When this switch is closed, it has a built-in LED as a visual indicator that current is passing through the circuit and allowing current to go to the motor.
Okay, so our bearings were selected on size, but we needed to do further analysis to see if they will fail. So what we did is we employed a basic dynamic load rating, which manufacturers will give us and tell us when 10% of the bearings start to fail. So the number that they gave us was 255 pound-force. So we needed to do our calculations and make sure that that number was below that to make sure that these bearings that we're going to employ wouldn't fail in the time that our machine will be in use, which we chose to be about 5 years. The first thing to do was to see what forces were on the bearings, which are depicted right here. With that, we were able to get an equivalent force, which is 12 pound force, and with other statistical values and the equation that I mentioned before, we were able to find that our calculated load rating was about 46 pounds, which is less than 255 pounds that the manufacturer said that it could take, which gave us about a factor of safety of 5, which is we're on the clear in there. So after doing analysis, we decided that, well, it's time to start doing a prototype. As you can see, the channels that we chose to use are a little complex, and we knew that we needed a lot of iterations. If we send this to a manufacturer, it would take a long time and it would be really expensive. So what we decided to do is to use a 3D printer, which uses inexpensive PLA, which is polylactic acid material. And as it's shown, as we have right here, it's shown in the picture, this is one of our first iterations. And as you can see on the model, the red is one of our last iterations after we tried different angles to see which one would actually fold this up correctly. And we also, for the circuit that Danny talked about, we had to do a couple iterations which we have on the table for the motor cover. And for a shaft, which we actually used aluminum to match the bearing that it's actually double seal enclosed and FDA approved. So the shaft fit the bearing, but we needed to know the distance, the size of the shaft insert. So when you put the belt, it doesn't hit the channels or it doesn't come out too much or it's not too low. So for that, we use 3D printing as well. And we also we're testing the surfaces to see if the friction will be enough to move the belt. And in this slide, what we can see is that for the ratings, we decided to use our school manufacturing facility, and we got aluminum rails, which are actually food safe, and even though it's a prototype, it wasn't too expensive, and it'll provide, it will be sturdy enough to hold everything together. It's 24 inches long because our research says that this will actually fit a subway line nowadays. And for the belt, we just use synthetic rubber simulate, which will provide friction as the real material that we would suggest for further machines, which is thermoplastic elastomer. Okay, and this, as you can see here and on the picture, this is fully assembled. As Danny mentioned, when you turn on the switch, you can see an LED that says it's on. You can just plug it to the wall, and it also includes things that I didn't mention, which is set screws and other screws used to hold the bearings together, and it's an easy disassemble for washing. This is a testing video of our early folding channels where we put a 5-pound load just to see if the belt and the rollers actually had friction, if the motor could indeed take the torque, and if the folding angle we were using would actually fold anything, because we didn't know really, and that's what we were doing the 3D printing iterations. This just shows that before it went in and after it went in, it folded about 3 inches, just simple testing.
Now, for final production, we chose different methods. For the plastic parts, we chose to do a molded injection, but for the frame, half moon, as well as the shafts, we chose CNC. Now, CNC aluminum, we chose aluminum as our main material for a number of reasons. One of them being its robustness, meaning this place is going to be in a high volume environment. If someone were to happen to knock it over, it would still maintain its integrity. Secondly, it's actually corrosion resistant, as well as when electroplating is used, it has a surface hardness that prevents scratching, which will deter bacteria growth. The second half of the manufacturing process, we use molded parts. For the narrowing channels, or the red channels you see on the model, they're going to be made out of acrylic. And the motor cover, the green device you guys see on my hand and in the model, is going to be made out of high-density polyethylene. Both are FDA approved, and both have distinct characteristics in which they're non-colored. So yes, we are going to market these for a subway line, but if any mom and pop shop wants to actually purchase these, they will be able to actually custom color it to their theme. This is the material analysis made on both the rails and the rollers. If I want you to please pay attention, the green rollers is signified by the green balloon, as well as the gray rails are signified by the gray rails. Both of them are made out of aluminum, and they show a significant strength, even with our exaggerated 10-pound load. So we have a minimum safety factor due to the rollers of 18.5, which is more than enough, and we're going to need them to provide longer life. Now, this is a cost analysis. This is using the same scheme as you see on the previous slide. The shafts are gold, and the green cover is all green. So each individual balloon signifies the material in which we suggest the final production be made, as well as the cost. Total cost for introductory unit is under $1,200. So, and the total cost of 120. This, if you do the math, it doesn't add up for this simple reason. The molded parts must actually have a negative, a mold. The molding is actually expensive in certain parts to 8,000, while each additional part only $6. What we did, since we're doing a run of 100, we divided that tooling cost among the 100 to get the actual total cost for units. So this is a cost if you were actually to run right now 100 units. As to further demonstrate our CNC parts, we decided to look up invoices from other companies. Obviously, we all know China makes cheap parts. There's no other way of saying that. But we chose the Chinese manufacturer and American manufacturer. American manufacturer first got both the Chinese and American manufacturers adhere to the ISO 9000 standard, which is the quality manufacturing standard of the ISO arm. While if you notice, an American manufacturer got $33,000, while the Chinese went under less than half of that. We eventually chose the American manufacturer for one simple thing, the turnaround time. We have a 7 to 8 day turnaround time with the American manufacturer. That's from date in to date received, as opposed to the 3 to 4 week turnaround time for the Chinese manufacturer. This data was extrapolated through experience and through shipping quotes received from other vendors. Now, this is a demonstration video which Shani will speak about.
Yes, so you can see in the demonstration, this is the final revision of our folding channels, indicated by the red, fully assembled, and this is using an actual sandwich. Okay, so now that we have a working prototype, the next part that we wanted to do was failure mode and effects analysis. Now, what this analysis is using inductive reasoning, and you go component by component to analyze what mode each component would fail at and what effect this has on the overall system. From our analysis, we concluded that the part most likely to fail is in fact the belt, okay, which we gave a severity rating of an 8, an occurrence rating of 3, which translates roughly to about 1 in 5,000 chance, and a detection rating of 2, which equates to approximately 99%, giving a risk priority number of 48. The same analysis was done for the bearing, the motor, possible incorrect placement of the sandwich on the conveyor, as well as electrical failures coming from the motor and the switches.
Okay, and for global component, like we said, we employ 3D printing PLA lactic acid, which is recycled, it's manufactured worldwide, and it's biodegradable. For future, we want this machine to have future, to do future things, like obviously wrapping this up inside a bag. So for these bags, we would recommend polynylon, which is also biodegradable. Like we spoke about, Subways and these restaurants are worldwide, so it's a worldwide market for this. Aluminum is sustainable, it's corrosion resistant, and it can be reused. And at the end, all these parts will be made in ISO standard facilities, which is as standard as known worldwide.
So for future revisions of this product, we have in essence laid the groundwork for work to come. We kept in mind a modular system for this very fact, so that anybody that wishes to add on to this it's easier. Okay, so we have some examples of things that we'd like to include at a future time. For example, the actual heat sealing mechanism, the housing, sorry, which you can retrofit 2 impulse sealers to fit into that. On the top right, we also have the stands, just in case you wanted to elevate it for whatever reason. We also have on the bottom left the crumb tray, which will slide right under the conveyor belt to catch any crumbs that may fall for a cleanliness aspect, as well as the cutting mechanism on the bottom right. And this video demonstrates the proof of concept in which we took 2 impulse sealers shown. The pink that you see is displayed by this. This is what the actual customer would get. Obviously the pink would be the sandwich, just for demonstration. We use 2 sealers so that when the sandwich is sealed on the first one, the next sealer closes the open-ended bag so that the process is continuous.
In conclusion, we have been able to achieve the task brought to us initially by our investor while still maintaining an eco-friendly environment by using the rapid prototyping of PLA, rapid prototyping by using PLA as a material. We also laid the groundwork for future improvement and future involvement while still examining the global aspect of both manufacturing as well as facility assembly. We are also able to incorporate different manufacturing processes within themselves to actually give a better all end product. Now, acknowledgements, we'd like to thank Dr. Benjamin Basil, Richard Todd Ziccarelli, Norman, our investor, Rosillo, Malika, who is not here, unfortunately, Dr. Carnegie, and Carla, who is, I just found out, a University of Michigan alum. And I'd like to open the floor for questions.
All right. Questions? Okay, Doc.
Okay, first question I have for you is what's melting temperature of PLA?
PLA?
Yeah.
PLA, it's actually, it's a range, it's from 190 to, I believe, 260.
So where does that put you relative to sandwiches coming out of?
Well, no, these are just for demonstration. The final product, the final narrowing channel will actually be made out of plexiglass, which will be able to send temperature that any sandwich will produce out of it. So this was just for prototyping purposes.
Okay, second question I have is, what is the distance from the beginning of your guide to the end of your conveyor?
Approximately 22 inches.
That's 22 inches.
Approximately.
So that'll hold your foot-long sandwich?
Yes.
That won't hold 2 foot-long sandwiches.
No, they're not.
So,
But this is to aid the actual consumer. When we did our research with Subways, they said that they wanted to actually mitigate the certain stations. The person taking your order, the person preparing your sub, and the person giving your order should be separate. Which is why in Rush, you usually see 3 or more. You never see less than 3 people in working behind the counter in Rush at a time. This is because they, during their examination, they found that it's easier for just someone to take the order, and the person preparing the sub just prepares the sub. This mitigates actually between preparing the sub and giving the sub. So this actually allows the person preparing the sub to go back faster without having to actually fold it, and allow the person giving the sub to fold it himself or herself. So this is actually a mitigation device to aid in that task.
okay. URL specifications, did you look at requirements for industry standard specifications for safety of appliances?
So could you repeat the question?
Okay, there are national standards for devices used. I'll use an example. This is going to be used in a space that's going to have water. You know, is this thing totally protected against having someone get electrocuted by the system?
What we did is actually, it's going to be fully enclosed with an actual bushing. You don't see it on this model, but we do have it in our drawings. What we do is we visit fully enclosed, but this is open so to show you fine gentlemen and ladies, the actual internal mechanism. It'll be fully enclosed, so no water should be able to penetrate inside. That is how we initiated our design.
Okay. And then the belt drive. Is there any safety on the belt drive, like clutch or something that would prevent someone from getting caught by that belt?
Well, the belt drive, we specifically chose a low torque motor. So if someone were to get caught, the motor would stall before
Stop.
anything happened. Exactly.
Okay. Then my last question, time improvement. You initially talked to us about how important the goal was around achieving a time goal. Did you do any work to show us that this system will improve that time?
No, we did not do any of that research. We did, however, do actually a speed test on the actual motor conveyor belt that's the lowest setting to actually improve. Again, this, with our system, you can upgrade the motor. It's actually upgradable, so you can, if you like, add a faster motor or a heavier motor in case, let's say you're in Wisconsin and they add extra cheese on your sub and it goes every 10. This way you can actually improve it and basically.
So I guess what he's trying to say is that this unit for the motor housing will be, in our modular design, it'll be just a unit that you could purchase to attach to it. So within this unit, from our end, you can fit it with whatever motor you'd like. We just chose this motor in particular because it's what we had available to us.
Okay, any other questions?
I'm having a real hard time with the concept of
Could you speak up a little bit for the
this.
rest?
I'm having a real hard time with the concept of this. If I watch your video, it takes seconds to do this.
What we would like to see, what we would like this to be taken is that in the future, we only did the folding part, so that's not much as it is right now. But what we want to see for the future is that, like Danny showed, for future components, is that you would add a sealer, you would add a cutter, and the people would actually make the sandwich, put it in there, and then just walk away and then start on the next sandwich, saving time. But this is a work in progress. We don't have the sealers. We couldn't make this automated as of now. We couldn't make a cutter automated as of now. So we're like opening the door so you can add things to it, and eventually then what you would do is just cut that step from the employee so you have more time. And if there was an employee that only did this, then you can cut that employee to increase revenue. But
Yeah,
as of now, it's just making the foundation for you to add things for the future. So it's fully automated.
Because remember this, why don't you run the flow process chart now and what it is after, so she'll probably have a better grasp. of
Well, I
what's
think
going
what you're trying, I think I understand what you're trying to say, is that as what Carlos said, initially we came onto this project as, treating it as an engineering firm. We're part of an engineering firm, an investor, outside investor, brought an idea to us. We, as engineers, decided to use our ethical knowledge, as well as our material analysis and every knowledge that we've acquired throughout the years here at FIU to achieve his goal to the best of our ability. So, if you're asking about that, I believe we've achieved that goal by making a machine that will fold this up. Now, for implementation purposes, that was out of the scope of our project. That was up to the investor itself.
Was the synopsis written at the same time that your report was written?
No.
The content of your synopsis does not correlate well with your report. You might want to look at that. You have a lot of formatting errors, a lot of grammar errors, a lot of content errors. Incoherent sentences, etc. You may want to take another look at your report.
Of course,
And Carla, you will be providing your evaluation report for the rest.
I didn't have a printer to print out 168 pages.
All right, are there any other questions or comments? Hearing none, thank you so much.